primary purpose of refrigeration is to eliminate the warm conditions under which destructive bacteria prosper and multiply, and by subjecting the bacteria to conditions of cold, to reduce their rate of activity and growth. The process of producing cold is the process of removing heat. Of the three effects of heat, refrigeration is chiefly concerned with two. The first effect, that of sensible heat, is one that causes a change in temperature as read in degrees on a thermometer. In this example, as heat is applied, the temperature of the water in the kettle rises up to 212 degrees Fahrenheit at sea level. At this point, the temperature remains constant, and the second effect, latent heat, is observed. The water changes state and becomes a vapor. Change of state may proceed in either of two directions. When a sufficient quantity of heat is absorbed by a solid, it passes into the liquid state. Upon absorbing more heat, the liquid evaporates and changes to a gas. When sufficient heat is withdrawn or released from the substance in its gaseous state, the gas condenses or changes back to a liquid. When more heat is withdrawn, the liquid freezes or returns to the solid state. For any substance, there are two distinct quantities of heat involved in changes of state. The first, latent heat of fusion, is the quantity of heat that must be absorbed by the substance in the solid state in order for it to change to a liquid. Or that must be removed from the liquid if it is to return to the solid state. The other quantity of heat, latent heat of vaporization, is that which must be absorbed by the substance in the liquid state in order for it to change to a gas, or that must be removed from the gas if it is to return to the liquid state. In mechanical refrigeration, it is the movement between liquid and gaseous states that is important. Absorption or release of latent heat does not alter the temperature of a substance while it is changing state. In this example, although the block of ice absorbs a certain quantity of heat as it melts, its temperature during melting remains constant at 32 degrees Fahrenheit throughout the change of state. Heat quantity is measured in British thermal units, or BTUs. A British thermal unit represents the quantity of heat required to raise the temperature of a pound of water 1 degree Fahrenheit. We know that when a liquid is heated to a certain temperature, it boils and changes to a gas. However, it is possible to cause the same liquid to boil at a lower temperature. This is done by controlling the pressure upon the liquid. The higher the pressure, the higher the boiling point temperature. The lower the pressure, the lower the boiling point temperature. It is through control of pressure that refrigerator temperatures are controlled. We know that heat will flow from the warmer to the cooler of two adjacent bodies, that the flow will be relatively fast while there is a large difference between the temperatures of the two bodies, and will become slower as this difference becomes smaller until it ceases when the temperatures of the two bodies have become equal. When a liquid changes to a gas, it absorbs heat which flows to it from its warmer surroundings. When these surroundings happen to be food in a refrigerator box, heat is withdrawn from it. That is, it is cooled or refrigerated. This is the rock-bottom basis of modern refrigeration. There are three methods by which transfer of heat from one place or body to another is accomplished. The first is conduction. When a flame is applied to one end of a metal bar, heat spreads through the metal, passing from molecule to molecule toward the cool end of the bar until the entire bar is hot. In the process known as convection, heat is carried along by the motion of a stream of gas or liquid whose function is similar to that of a conveyor belt. In conduction and convection, heat is transferred through or by matter. The process of radiation involves the direct transfer of heat in the form of waves, without need for a medium for the heat to move through. Refrigeration makes use of all three methods of heat transfer in removing heat from food items to a liquid cooling agent. Heat travels between the food and the cooling unit wall, both by means of radiation through direct waves and by means of convection through air circulation. The heat passes through the cooling unit wall to the liquid by conduction. The substance which soaks up heat during evaporation to create coolness is called a refrigerant. Its function is to remove heat from one place, leaving that place cool, and to discard this heat elsewhere while it is being changed back to a liquid. To produce refrigeration, all that is necessary is a refrigerant that functions in terms of the physical facts and processes already described. Refrigeration would be adequately achieved if we placed a liquid refrigerant in a box and provided an outlet for its escape following its change to a gas. However, at this point, several practical problems must be solved. To minimize the amount of outside heat that enters the refrigerated storage space, the walls of the box are filled with insulating material which does not absorb heat readily and is a poor heat conductor. A second practical consideration is the cost of the refrigerant. For economy, the refrigerant must be saved, stored, and returned as a liquid to be used again. And this process must be made automatic. This is the purpose behind all the electrical and mechanical devices which we identify with modern refrigerating systems. There are two principal refrigerating systems, the compression system and the absorption system. The basic difference between them lies in the source of the energy that drives them. The compression system operates on mechanical energy produced by a motor-driven compressor. The absorption system uses heat energy supplied by a flame or some other source of heat. The compression system, activated by a compressor, will be described first. It is divided into the high and low pressure sides. The high pressure side is that portion of the system through which the refrigerant travels under high pressure. This side starts at the discharge valve of the compressor and includes a condenser, the receiver or storage tank, and the liquid line. The low pressure side is that part of the system through which the refrigerant moves under low pressure. This side starts at the expansion valve, which divides the high and low pressure sides and includes the cooling unit or evaporator, the suction line, and the suction valve of the compressor. The compressor is essentially a cylinder in which a piston works. This is the course of a refrigerant through a typical compression cycle. The refrigerant, in the form of a gas under low pressure, is drawn from the suction line into the compressor. The gas enters the cylinder through the suction valve as the piston moves on its downward stroke. When the piston moves upward, the pressure and temperature of the gas rise. The gas is compressed and is finally pushed through the discharge valve into the condenser. The refrigerant enters the condenser as a high-pressure gas, and its temperature is higher than that of the air or water cooling the condenser. As heat flows from the gas to the cooling agent, the gas condenses, changes to a high-pressure liquid, and passes into the liquid receiver or storage tank. From the receiver, the high-pressure liquid refrigerant passes through the liquid line on its way to the cooling unit. The high-pressure refrigerant must now be reduced to a low-pressure liquid so that it can evaporate at a low temperature. The refrigerant passes through an expansion valve which divides the high and low pressure sides and controls the flow of refrigerant into the cooling unit. The refrigerant enters the cooling unit under a reduced pressure caused by the suction stroke of the compressor. It evaporates, absorbing heat from food in the refrigerator and providing what we know as refrigeration. The refrigerant, now a low-pressure gas, is drawn through the suction line back to the compressor, completing the cycle. This, then, is the cycle of changes of the refrigerant as it moves continuously through the compression system. The absorption system is based on principles developed in a famous experiment conducted by Michael Faraday. He sealed in a bent test tube a compound of silver chloride, a white powder, and dry ammonia gas which had been absorbed by the powder. He heated the end of the tube containing the powder and at the same time cooled the opposite end of the tube with water. Ammonia vapor was released during application of heat and was condensed in the cool end of the tube. When the flame under the powder was extinguished, vapor that had not been liquefied was reabsorbed by the powder, reducing the pressure on the liquid ammonia. The liquid ammonia began to boil, changed back to a vapor, and was reabsorbed by the powder. The end of the tube containing the boiling liquid was intensely cold, the evaporating ammonia having drawn heat from the nearest substance, the test tube itself. The driving force in the absorption system is heat, and a heater and generator take the place of the compressor. The generator contains an absorbent, a liquid or solid which has absorbed the refrigerant. Water passes through a coil to cool the absorbent and permit it to reabsorb the refrigerant at the proper stage of the cycle. A simplified diagram of the system is filled out by a condenser and a tank which serves as liquid receiver and cooling unit. Check valves guarantee the movement of the refrigerant in only one direction. The cycle begins when heat is applied to the generator, releasing the refrigerant as a gas from the absorbent. The gaseous refrigerant travels upward to the condenser, which is cooled by air or water. Here it is liquefied. Its heat is dispelled, and it flows by gravity to the cooling unit. As the liquid refrigerant accumulates, the float rises until it reaches an electrical contact point, setting off a device which automatically turns off the flame of the burner. The same device also sends a stream of water through the coil in the generator. The absorbent which surrounds the coil is thus cooled. Two processes now cause the refrigerant to evaporate. One is the transfer of heat to the refrigerant from the food near the cooling unit. The other is the power of the absorbent, when cool, to reabsorb the refrigerant. When the liquid level drops sufficiently for the float to reach the lower electrical contact point, the burner is automatically lit, heat is once more applied to the absorbent, and the cycle is renewed. In this way, an intermittent absorption cycle is produced through the alternating application and withdrawal of a flame. The principles of refrigeration are physical principles applied as follows for the purpose of removing heat and reducing temperature. First, mechanical refrigeration rests on the ability of a refrigerant to absorb heat while changing from a liquid to a gas, and to release that heat while returning to the liquid state. Second, when the pressure on a liquid refrigerant is reduced, the liquid boils at a lower temperature. Third, the transfer of heat from food items or other warm surroundings to a liquid refrigerant involves three processes: radiation, convection, and conduction. With the introduction of a refrigerator box insulated against outside heat, the elements of refrigeration are ready to be brought together in a refrigeration cycle. In the compression cycle, the compressor forces the refrigerant through the system. The liquid refrigerant in the cooling unit absorbs heat, thereby cooling its surroundings, and changes to a gas. The gaseous refrigerant loses this heat in the condenser and changes back to a liquid. In the absorption system, heat energy provides the initial movement when the refrigerant is released as a gas from the absorbent. After losing its heat and liquefying in the condenser, it moves by gravity flow and collects in the cooling unit. The refrigerant then absorbs heat from its surroundings, changes to a gas, and is reabsorbed by the absorbent. These are the principles of refrigeration. Understanding them is basic to good refrigeration practice.